All right, welcome everyone. This is Sergio Castella from Z Alpha, and today we're here to talk about NeurIPS 2022. So, as some of you might know, NeurIPS 2022 is around the corner. It's going to happen on the week 28th of November to the 4th of December. Nothing less, nothing more than 2672 main papers on the main conference. So that's 63 workshops, 7 invited talks. So it's quite a big thing. So you might not know where to start. So at Z Alpha, we've made this really cool semantic map to help you navigate it, and we're gonna just look at it a little bit. Before we dive in, I wrote a kind of a blog piece outlining a bit of what I thought were the 10 more important topics and 5 papers in each of those topics that you might want to start checking out. And with a bunch of resources, you can go to our website and read that out as a more kind of linear way of going through it. Check that out, links in the description, everything. That said, there's a bunch of about a dozen titles. So we're gonna talk about language models and prompting, diffusion models, not only for vision, but for other stuff. Self-supervised learning, which is also kind of also quite overlapping with the other topic. Is pretty much like a topic in all machine learning papers nowadays. We have graph neural networks, we have reinforcement learning, we have brain-inspired stuff. NeurIPS is also home for a lot of publications that come from the more neuroscience tradition, and that's also really cool. We have out-of-domain generalization stuff, learning theory, like the more mathy things, adversarial robustness, federated learning, compression. This is a bit of a more kind of a mix of things that didn't quite fit in other camps, but are still very interesting to talk about. And finally, datasets and benchmarks. Okay, so what you see here is actually not only all the main conference papers, but also the workshops and the dataset track. So if you go to NeurIPS Open Reviews, you're gonna see that not only the main conference, but also you have workshop and track, which is basically the dataset track. So this actually includes all of the papers, which, if I'm not mistaken, this is almost 3,500 papers. Okay, so what you see here is a semantic map of these almost 3,500 papers, and then the size of the bubbles here corresponds to different things. Right now we have a metric that we created that's called impact, which kind of combines things like Twitter popularity, citations already that these papers have accumulated, because a lot of these papers have been on archive for many months, the author influence, like how their age index and how popular they are. So we kind of mix a lot of these signals to kind of get a early sense of how impactful papers are gonna be. So the first thing to note about a lot of these papers is they're gonna be actually kind of old. I don't know, you probably remember about Imogen, right? So this was released on May 2022. So you're going to see a lot of papers that have been on archive for more than half a year and were very quite popular. But on the flip side, a lot of these papers are going to be much more high quality than what you're used to on archive. So that's really, really cool. All right, that said, let's just jump right into it. The first cluster that I want to look at is this whole language model thing. Arguably, this has been the most, influential part of AI in the last couple of years, especially since the introduction of GPT-3 in 2020. And a lot of these papers are looking into new prompting techniques. Perhaps the most famous one, or the one that you should probably not miss, is this chain of thought prompting elicit reasoning in large language models, which is this paper from Google. Basically shows how, so if you prompt the model to include steps of reasoning before they answer the final output to a question, the reasoning abilities go up, and it's much more faithful and much more robust. And this is pretty cool because it doesn't require any retraining of the model. It just happens. It's kind of a trick that you can add to your prompting that makes your models better. And I feel like this is a huge trend in large language models literature. There's a whole lot of kind of low-hanging fruit of you have these massive pre-trained, very powerful language models. How can you squeeze a lot of performance out of that without really touching much on the basics? Another very interesting one that you should not miss out is this Flamingo. This was also really popular from DeepMind. Yeah, it's a multilingual vision language model. DeepMind made a big fuss out of that. It's a really interesting paper. They basically trained this whole model on vision and language, and at the time they published it, they had state-of-the-art performance in stuff like zero or few shot object detection when they fed the model with an image and then they ask it to complete. So like the prompt was an image and the model output some type of text that included classes of like animals and all that kind of stuff. Oh, another one that was also quite popular. Yeah, this one, which was the solving quantitative problems with language models. This model is also called Minerva. Yeah. So the large language model pre-trained on general language data and further trained on technical content. And yeah, they basically showed how large language models can also do a lot of math reasoning if you give them the right data, which is kind of also like one of the big topics in these large language models research. Invest in the data that like the large scale data that you're training on, that pays off really well. And finally, we have Transformer Memory, the Differentiable Search Index, extremely interesting paper in the space of information retrieval. This is also arguably very close to the self-supervision camp, but they basically train a language model directly to output document IDs based on a query. So basically how this would work is a search engine is you type in a query and then in an autoregressive way, the model outputs a document ID or some document representation of the document that's most relevant to that question. And how they do that is they get parts of a document and then they train a model to kind of generate the document ID based on that. So the actual method is much more complicated, but that's the gist of it. And I think it's super, super interesting. And it has also generated follow-up works. Even in the conference, there's this neural corpus indexer for document retrieval, which is kind of a follow-up work on that. And there's a couple of other papers. Anyway, we don't have time for all of this pile of law, legal data set. Autoregressive search index search engines is also one pretty similar to the differentiable search index one. Oh, this one is also pretty big, from OpenAI training language models to follow instructions with human feedback. They basically have GPT-3 interact with human annotators, and with that type of feedback, they improve the performance of the models. And this thing is called Instruct GPT. That said, on to the next thing, diffusion models. I mean, arguably, if there's one new cool kid in town for this year has been diffusion models. I mean, ever since DALL-E 2, which was, when was it released? DALL-E 1 was January 2021, but DALL-E 2, April 2022. So ever since then, there was like, Google's Imagen. There was this month that was crazy. There was Google's Imagen, then the Stable Diffusion that everyone was talking about. There was Google's Sparty as well. Not all of them were diffusion models, actually, disclaimer, but a lot of them were, like Imagen. And now diffusion models, since they became very popular a couple of years ago when they, I think it was like in early 2021 when they beat GNNs, generative adversarial networks, in image generation. They became super popular, then they exploded. And the cool thing I think is like it feels like text to image generation is kind of solved. I mean, it's not solved, it can be improved, but a lot of this research is now pivoting towards more challenging stuff like video generation and using diffusion models in other domains, like even text generation or molecule structure generation. So I think that a lot of the cool stuff revolves around that. So the first one that we have to highlight is Imagen, which is like the paper is actually published at NeurIPS, Google's version of DALL-E 2, which had interestingly quite a few different design decisions, like the embedding, like the encoding of text is by a frozen language model, and then they have a separate diffusion model with hyper resolution that generates images, which is quite a different thing from the clip-based embeddings that OpenAI uses. Then we have supervised object centric learning for complex and naturalistic videos. What else I think would be interesting to highlight here? Yeah, this one, flexible diffusion modeling of long videos that is able to sample temporarily coherent videos over 25 minutes in length. And currently developed the first denoising diffusion probabilistic model based video generative models. Yeah, there's other stuff. It was kind of funny with video diffusion models. Everyone knew that they were coming, and like suddenly a bunch of people like from Meta and other labs put out stuff about it. Yeah, so totally expect more stuff on diffusion models. Sound spaces, diffusion to simulate sound in 3D, and then so there's this other big bubble here, simple robust lidar camera fusion, segmenting moving objects via an object-centric layered representation. The next topic that I wanted to talk about was this self-supervision camp. This is mostly self-supervision for computer vision. It's like it's kind of funny. Like now, all language model, like everything has self-supervision baked in it. So it's like kind of almost not that informative to actually talk about self-supervision. But anyway, we have these video mask autoencoders. They basically show how to make the best video representations with masking and self-supervised learning. Then we have this one that is quite related. Mask autoencoders are spatiotemporal learners. We have the inception transformer, new transformer architectures, quantity not quality interaction between dataset robustness. Introduce a testbed of 6 publicly available data sources, blah, 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 to investigate how pre-training distributions induce robustness in clip. We have stuff about dataset distillation, and of course we have stuff, and there was this paper that I quite liked about data augmentation, which looks at how data augmentation compares to adding samples from the training data set. All right, next topic that I want to talk about was, here it's called molecular optimization. It's arguably, there's a lot about GNNs and actually using neural networks for solving partial differential equations and like physics simulations, this whole space of predicting shapes of 3D molecules. That has been also like an explosion of like a lot of papers in this domain that especially, since the introduction of AlphaFold, a lot of people are paying a lot of attention to this, and it shows in the NeurIPS lineup of papers. So for instance, we have this magnet mesh agnostic neural partial differential equation solver. We have torsional diffusion, once again, like diffusion model applied to conformal generation. This works on predicting the shape of molecules in 3D, message passing, more graph neural network stuff. So the ones that I highlighted before that I thought were quite interesting were these zero-shot 3D design by sketching and generating. Yeah, they basically speed up a lot of the drug design ML pipeline by having 2 differentiated steps. So they use a combination of retrieval from a large-scale molecular database to reduce the need of simulation, and then a second step of generation of molecules. Then another thing that I want to highlight is torsional diffusion models for molecule conformer generation, this whole space of partial differential equation solvers, which might have impact in the whole physics simulation space. Message passing in higher order. So normally in message passing, you only have like neighboring nodes talking to each other. So this paper investigates kind of the generalization when you can have modeling of higher order of skipping n nodes in the connection. And finally, this few-shot relational reasoning by connection subgraph pre-training. The next big topic is reinforcement learning. Reinforcement learning is huge in NeurIPS. So we have these 2 massive bubbles of reinforcement learning and then efficient reinforcement learning. So what happens is a lot of reinforcement learning research is preoccupied with the whole issue of how do we make reinforcement learning agents more efficient, learn faster, learn from fewer samples, learn more robustly. That said, one of the very interesting sort of trends that you can see in the reinforcement learning space is that a lot of the language modeling research is kind of like feeding into the reinforcement learning and vice versa. So there's kind of like, for instance, like I said, in the previous paper of InstructGPT, where you have ideas from reinforcement learning on humans giving feedback to the model on what is good generation, what is not so good generation, and the model kind of updates its policy of generation. And then there's papers in reinforcement learning that use language models as some kind of bootstrapping for the policy to break this inefficient exploration phase. For instance, you have this using natural language and program abstractions to instill human inductive biases in machines. How I describe the gist of the paper is meta-learning agents can learn human inductive biases through co-training with representations from language descriptions and program induction. Then we have the Mind Dojo, the paper from DeepMind, which defines a way of generating dataset for offline reinforcement learning. So basically, a big problem of reinforcement learning is really hard to have a large-scale data set of like video and actions data. So what they do is basically only from videos from Minecraft, they train a model to label those videos with actions, like what key presses are like the players playing. And then they use that to generate from massive amounts of video online. So then you have like video paired with actions, and then you can train an agent with imitation learning to predict the next action based on the previous action. Then you do imitation learning on that. And then you have a pretty solid agent performing well without any online learning, without any sort of interaction with the environment, which is notoriously hard because you have a lot of problems with inefficiency. This was a very popular paper that is also presented in NeurIPS. Then we have a very cool application of reinforcement learning around chip design. So that means like silicon chip design, like how you place components in a chip and how you kind of arrange things so that, there's like the memory latency and kind of all of these things. You minimize a bunch of trade-offs. This paper to make Monte Carlo 3 search efficient by kind of spending different compute budget on different states based on how hard they are. And then finally, this trajectory balance improved credit assignments in GFlow nets from Bengio's group, which looks at improving the credit assignment problem, which is this problem of like when you have a reinforcement learning agent that does a trajectory and only at the end of the trajectory you get a reward of like, I don't know, you play a chess game and then you win or you lose, but there were maybe like 50 actions within that trajectory. How do you know which one of those actions is most responsible for that final reward, a positive reward? So that's a big problem in reinforcement learning. So in this paper, they define a new objective based on trajectories that apparently makes this credit assignment problem a little bit more tractable and easy. On to the next topic that I wanted to talk about was brain inspired. Like I really don't know much about neuroscience, if I'm very honest, but there's quite a bunch of papers at NeurIPS that try to kind of tie back to stuff in the brain. The things that I highlighted here related to stuff about predictive coding, which is a really popular hypothesis for explaining how the brain works. So this paper experiments how backprop and predictive coding compare, especially in neural network topologies where backprop doesn't work, where there's kind of like backward connections. Then we have stuff about spiking neural networks, self-supervised learning on neuroimaging data, which is important to learn good representations about neuroimaging data. Node perturbation learning, which is also another kind of brain-inspired backprop alternative type of thing to neural networks learning. And finally, this curriculum learning in teacher-student networks, which comes a bit more from the psychology literature background. All right, the next topic that I wanted to highlight was out-of-domain generalization. This is a super interesting one. I think that it's like particularly fascinating, especially conceptually, but it has still struggled to gain a lot of traction. And what has happened, in my opinion, with this whole out-of-domain generalization field in machine learning is that it still lacks a lot of standardization. Everyone has a really good sense of what out-of-domain means intuitively, but when it comes to making benchmarks for it is very hard. So what you have is a lot of papers that propose new methods and then they can only test on toy data sets of generalization, or like the benchmarking field is not so established. Nonetheless, there's a lot of interest in this topic, and also like something that's very closely related is the whole thing about causal learning. Like a lot about learning out of domain generalization is about learning robust representation, learning about robust models of the world that capture the causal structure of things that will let a model predict in novel circumstances, right? So you have, for instance, these large-scale differentiable causal discovery on factor graphs. We have this like very like interesting paper which looks at how just averaging models boost performance in domain generalization, which is one of those papers that kind of proposes a very pretty simple thing that shouldn't work so well that kind of like works kind of annoyingly well. Yeah, this paper really good. It's a sort of overview or like you could say a survey of the space of out of distribution generalization. Like I said, lacking standardization. So this paper tries to kind of like put a lot of that together and get some of that standardization. This is a modular architecture enough. This paper also is quite a survey-ish like paper that proposes a new benchmarking for this type of architecture that have modules that interact, not necessarily sparsely, but like independent models that interact in some way, and the kind of like hand-wavy idea behind them is that they're going to learn more robust and disentangled representations that more closely capture the causal model of the world. So this paper proposes new ways to quantify these models, which is also a paper from the Joshua Bengio's group that I think is working a lot on this, and that has been putting a lot of research papers out that are very interesting in this domain, but they don't make it into these like big benchmarks, but they're very interesting in my opinion, at least conceptually, into making progress in the broader sense of artificial intelligence. Anyway, and finally we have this paper on tabular deep learning. The tabular deep learning is this, I wanted to include this because tabular data is one of those things that has resisted still the deep learning revolution in some ways, and you keep seeing papers about a deep learning technique that outperforms everything else on tabular data, but it's hard to make it robust. So this paper proposes to represent numerical features as vectors instead of numbers. So basically, if you're interested in the whole tabular data stuff, you should also check that out. All right, on to the next part of the map, which is learning theory and generative modeling theory. So perhaps, unfortunately, I'm not well versed into the whole theoretical machine learning stuff. It's kind of a meme at this point, right? That a lot of the machine learning theory is just kind of confirming or finding some sort of formal explanation for something that was known empirically for many, many years. But still, it's quite important to, especially to kind of improve our intuitive understanding and have like more grounded intuitions about why things work like they do, why things converge in a certain way or another. So it's definitely like a very important camp within NeurIPS. So the first one that I wanted to highlight here is a one that many can resonate with, which is this thing about why large batch sizes are needed in contrastive learning. If you've read some of the literature on contrastive learning, you're gonna know that batch size is like one of the most important hyperparameters when you're doing in-batch negative sampling in contrastive learning. And this paper looks at a bit on the theoretical side on why that is. And kind of intuitively, it makes sense that you need more numbers. And kind of like this is one of those things that's kind of empirically everyone had like good, like more or less intuition about it and was like, yeah, sure, that's how it works. So this paper puts a bit of more robust Bayesian analysis behind it. Then we have this is out of distribution detection learnable, which looks at from this theoretical standpoint, how is it even possible to know whether a data point comes from out of distribution or not in various situations? The kind of gist of it is like there are circumstances under which it's not possible, like formally not possible, but in the real world problems, this is not going to be a problem most of the time. So whatever, you're fine. Then there's a couple on automatic differentiation. What happens when you apply automatic differentiation on not smooth enough functions, and then this autodiff on implicit differentiation, which is quite interesting. I'm not sure how much of an application this is gonna have, but it's very interesting. And then finally, this gradient descent, the ultimate optimizer, where they find a way to use gradient descent to optimize also hyperparameters of neural networks, and like have everything end-to-end optimizable, which I'm still a bit skeptic. I feel like a lot of the training of large neural networks still needs a lot of kind of human, high-skilled knowledge and accumulated intuitions about what it takes to train these large neural networks, which is like almost like alchemy of small tweaking. It's a craft that very few people in the world now know how to do. I'm still a bit skeptic that you can automate like properly, fully end-to-end this, but still is a very interesting exploration on optimizing hyperparameters. So as we reach almost the end of our exploration, the two last clusters that I wanted to look at is like this whole area at the bottom, which is like federated learning is this small, it's not a niche, but so the federated learning is this idea of kind of having peers do learning where the learning is not centralized in one compute node, but there's a bunch of peers collaborating with data, with training compute and all of that. And that is often merged with ideas from differential privacy, which is this whole idea of how you can have people collaborate on learning and sharing data without having this data be directly traceable to any specific individuals. No ideas that you can learn from data without revealing stuff from particular people. Then we have the space of adversarial robustness, which also has been really, really, really old in machine learning. This is super, super important when you want to deploy models where there's going to be adversaries that can have bad faith, potentially trying to hijack your models. And finally, also a very, very, very important one, which is the whole space about quantization pruning and making models more efficient, making them able to run on smaller hardware, making them run fast. So in this camp, I have some papers on data pruning, federated learning, adversarial robustness. This one that's really cool. On-device training using under 256 kilobytes of memory. And finally, these pre-trained adversarial perturbations. And last but not least, we have datasets and benchmarks. So you don't really see that in this semantic map. And the reason is the topics that datasets and benchmarks at NeurIPS cover are so broad that these papers are actually all over the place in this semantic map. But you can go to, like I showed you before, on these datasets and benchmark tracks. I think there's 137 papers. From those, I highlighted 5, which is first this Lion 5 billion dataset, which is the largest open dataset for image and text pairs, which aims at improving the training of multimodal models, or like models such as text to image. So it has more than 5 billion images and text pairs. We have this dataset condensation benchmark, which is a really cool concept that I didn't know about before, which revolves around the idea of a lot of benchmarks and datasets are massive these days. So how can you like compress those datasets so that you can have kind of like more lightweight evaluation that still captures the richness and like what makes datasets harder and what makes them good at evaluating things. So that's really interesting. So then we have this near world benchmark for offline reinforcement learning, which is super cool. Is this thing about evaluating offline reinforcement learning often has a problem that it doesn't translate that well to when you do online learning in a kind of real interaction based environment. So this paper claims that they have a benchmark that kind of gets a little bit of the best of the both worlds and gets almost real world benchmarking in an offline fashion. These textual backdoor learning frameworks and benchmarks is this open source toolkit for evaluating how vulnerable a language model, for instance, is to textual backdoor attacks, which is this thing where you inject things into prompt and then highly affect what the output is going to be, which is a very important vulnerability that now, as we're seeing a lot of language models deployed as APIs and become public in some way or another, this is going to be extremely relevant. And finally, this peer, a comprehensive and multitask benchmark for protein sequence understanding, which is a benchmark around the whole problem of protein folding and protein structure and protein structure generation and like understanding this whole space. Yeah, and that's pretty much it. I mean, of course, it's not at all a comprehensive look at what NeurIPS has to offer, but I hope it's a good start. Like I said, you can go to our blog and read these papers. So one of the things that I'm most proud of actually is this whole links thing. It took me a while to do this actually. So basically here for each paper, you have the open review link, the virtual poster link on the NeurIPS conference page that you need to be signed into the NeurIPS virtual conference to be able to see that. And finally, we have this more like this paper, which triggers a search on our platform to search for similar papers to, for instance, here we have solving quantitative reasoning problems with language models. So this will find you papers that are similar to this one at NeurIPS in 2022. Definitely use that to navigate the conference. All right, so that's pretty much it. Thank you for watching. Follow us on Twitter on ZetaVector, and I'll see you in the next video. Thank you.